Okay, we want to look at some of the key ideas now at existence level. And one of the first key ideas that we need to think about is data and how accurate our data is. Because if we've got data that's not very accurate, then that's going to lead to our conclusions and analysis being inaccurate as well. So, for example, if you were to measure the heights of students and you were rounding all of those numbers to the nearest 10 centimetres, then that's not going to be as accurate as using the original measurements would be. Okay, so there's different kinds of accuracy issues that we could look at. There's issues about duplicating data. So you've got the same student has been entered twice or 3 times. There could be missing information, and this is when people don't necessarily answer every single question on your questionnaire form. They might leave some questions out. We might have inaccurate information. Okay, so like I said, we might just be talking about how many text messages did you send yesterday? And I can't remember exactly the number of text messages I sent yesterday, so the information I give will not be accurate. And sometimes there'll just be incorrect information. If I didn't have my cell phone and somebody came to me and asked me, how many messages did you send yesterday? I might feel embarrassed to tell a total stranger that I don't have a cell phone, and so I might just make up an answer. Okay, so we're going to have these instances of bad data, and you can never avoid it. It's always going to be present, but hopefully it's going to be as small as possible. So how big an issue is this really? Well, they estimated that last year in the US, it cost US companies over $600 billion in terms of having made bad decisions and the cost of doing business when your data is not as good as you need it to be. Okay, so the more accurate your data is, the better you've got results and conclusions. Another key idea around, if we're at excellence level, is looking at what happens with our measures of centre. So when I'm talking about the first graph at the top is our normal distribution, and in our normal distribution our mean, median and mode are all at that same point. So let's have a look start within our mode. So I've got the mode of the first one. Now the second graph, the data is getting a little bit more skewed towards the left, so the mode is still that highest peak. The third graph, again, the distribution is now getting more skewed to the left, the tail's getting longer on the left, but the mode is still where the highest peak is. Okay, so for each of these distributions, the mode is the highest peak. Now let's have a look at what happens to the median. So in our normal distribution, the mode and the median will be the same. With a left skewed distribution, the median moves down a little bit from the mode. It's just a little bit to the left hand side of it. With a more skewed distribution, that median moves over a little bit more. Not a lot, but just a little. Now let's have a look at what happens to the mean. So for our normal distribution, the mean is right bang in the middle. As we start getting skewed distributions, that mean starts to be pulled even further down towards the tail. And the more skewed it is, the more that mean is being pulled down towards the tail. So the reverse would also be true of right skewed distributions. That if you've got a right skewed distribution, the mean is being pulled up towards the tail. Okay, so from those ones now, if we look at them, which is the most stable measure? The one that's going to be the best representation. The mode is very simplistic to use, so we don't like to tend to use the mode. But if we were to compare the mean and the median, with a perfect normal distribution, they're both the same. We could use either, so let's use the more complicated measure, which is the mean. But if you've got skewed data, then the median is the more stable measure of centre. And that's why back in the analysis, when I ask you to compare the centre, I'm always asking you to compare what the median are, not compare what the means are, because it makes a difference if we've got skewed distribution. Okay, so that's 2 key ideas. Here's a third one. In our analysis, there's the 3 features that you write up about: shape, centre and spread. So here's a fourth feature that we could talk about, looking at the middle 50% and looking at the overlap or the shift. So if I just colour in there in red, just to highlight for us, the middle 50% of the female bag weights. And I can say, I notice that the middle 50% of those female bag weights lies between, and the lower quartiles at 2,000 and the upper quartiles at 5,000 grams. So I can write a sentence just telling me where that middle 50% is. It's between here and here. I'm going to do the same now for my male. So I've coloured that graph in blue, and I'm going to write a sentence saying that the middle 50% of their male bag weights is between 1,600 and 5,000 grams. So just a statement there. Now I need to do the comparison part. So what I'm doing here is I'm saying I'm noticing that the female bag weight is shifted slightly to the right. So watch what happens. I'm just going to take if you look at the graph, I'm going to take that red box of the females and I'm going to just drop it straight down onto the males. Okay, you see that what I did? I'll just show you again. I'm just taking that box and dropping it down. So when we drop that down, you notice that the males is slightly to the left hand side and the females is slightly moved up to the right, and that's what I mean, there's a slight right shift of it. And then if I also go on to look at that, look at the colour in the middle, that's a combination of the blue and the red, and there is a lot of that colour. There's a teensy little bit of red at the top end and a little bit of blue at the bottom end, but that mix of colours in the middle, there's a lot of overlap. And so that's what I'm going to say in my sentence here, is that the female bag weight is shifted slightly to the right, and there is a lot of overlap in the weights of the bags. Okay, and that's another piece of evidence that leads towards maybe I don't have enough evidence to say that these medians are different enough. The last feature that we can look at in the analysis is to talk about unusual features. Now this is where you've got to be very, very, very careful, because these need to be very obvious. I don't want you to be saying this unless you're absolutely sure, because too many students make bad mistakes with this and then get it wrong. So one of these unusual features we could have is something called an outlier. So here's a graph, and this is looking at the weights of male university students. And you'll notice right up the top there, at about 125 kilograms, there's a single male's weight. Now that male's weight is a long way away from the rest of the data, and that's why I can classify it as an outlier. Okay, the other data values are all reasonably close together. There's no other values I would call an outlier. It has to be a very, very long way away to be called an outlier. And then I could write a sentence about it to say I notice that there might be an outlier with a weight of around about 125. Okay, and again notice the wording, there may be an outlier or there's a possible outlier. I'm not saying for sure. When you get to university, there's actually some tests that you'll be taught about how to tell for sure whether you can classify it as an outlier. At the moment we're just going that visual idea of, is it far away from everything else? The other unusual feature we can look for are clusters. So if we look at this graph here, which is looking at time and paid work, there are kind of some groups going on. I've got a group down the bottom here around 0. So a group that didn't have many paid hours of work in the last week at all. Then I've got a group in the middle around about 20 hours, and then I've got a group up further around 40 hours. What do they represent? Well, the 20 hours probably represents the people that are working part-time, and then the 40 hours a week are those that will be working full-time, and because often a salary job is classified as a 40-hour week. So now I could say I've got 3 clusters, and I can explain what they are. But again, be very careful with trying to say that there are clusters, because it could just be random sampling. Random sampling and representation, reminding you that if we've got a random sample, that will give us data that's representative. Okay, and that means that we've got a lot more trust and accuracy in our analysis and conclusion. So the representation comes from the fact that we are taking a random sample. If we take a biased sample, we're not getting representative data. Okay. Now the last key idea here is about sampling variability, and particularly what we looked at before was what happens if I take another sample. But what I want to investigate here is what happens if I change my sample size. So if I've got more information about something, then I'm going to be more accurate. So as my sample size increases, the accuracy increases, which is a good thing. But we need to think about what happens if I take a bigger sample to my data, okay, what happens to my summary statistics, and what happens to my conclusion. And I'm just going to show you a demo. Let me just be with me for 2 seconds. So what I've got here is this is a population distribution of all heights of girls age 12. And I've got basically a dot plot, which is turned into a bar graph, and the box plot. Now this is because it's a population, we would love to know the population, take a census, know everything about everyone, but we don't know that. We don't get to see this population. So I'm going to just kind of, it's faded now into a dull grey background because that's the population that we don't get to see. What we do get to see is a sample. Okay, and so I've got 3 different samples here. I've got n equals 10, sample size of 10 students, girls aged 12, and their heights. Then I've got n is 100, sample size of 100, and a sample size n equals 1000. And I've got the graphs that I'm drawn there. Now every time I press the button, we're going to take another sample and we're going to see what graphs come. So just start by having a look and seeing what is happening as I take another sample. The shapes are changing a little bit. The medians are moving around a bit, the whiskers are moving around a bit. So if I take more samples, okay, if I take another sample, then things could change. But now what I particularly want to know, and I'm going to show you another demo, is what happens if I take the sample size changes. So what I've got here is I've just taken a sample size of 10 and I've drawn the graph in black. Now you can see I've got some red lines showing, and that was where the first sample was, is the red lines, and you can see there's a faint blue line in the middle, and that's where the previous median used to be. So I'm going back to here, so look at where the median is then, and now I've drawn a blue line where that is, and where the box was, the upper and lower quartiles, I've drawn those around in red. And so I'm just going to keep taking samples here. Okay, the blue lines are the medians, the red lines are the upper quartiles. And you can see I'm also taking samples now of 100 and 1000. Okay, so what do you notice? Okay, and I'll just jump over to, this is the graph where it's doing it continuously now. It's that same graph. What do we notice? Well, down the bottom, this would be the population. If I've got a small sample size, a sample size of 10, we'll notice that those blue lines, there's quite a variation in where the median might be if I take another sample, isn't it? And the upper and lower quartiles, there's quite a range going on there. If I increase my sample size to 100, the medians kind of are a lot closer together. Each sample, the medians are lying within that range. And my upper and lower quartiles, again, the range now is getting a bit smaller. Now let's look at a sample size of 1000. The spread there in the medians is getting much, much smaller now. Okay, it's much, much more accurate. Same with the upper and lower quartiles. Equally, if I look at, this is looking at a sample size of 1000 now if I'm trying to compare 2 groups, and we notice that the medians now are very similar positions. No matter how many different samples we might take, they're all going to be quite similar. There's not going to be a huge amount of variation between those estimates, and that's what we want to see. So if I go back to my lovely slide here, what happens if I take a bigger sample? I'm going to get more data, a lot more data. More data means more information, which means more accurate. My summary statistics, the median's going to become more precise. The mean's going to be more precise. My upper and lower quartiles are going to be more precise. And in particular, my interquartile range is going to get smaller. There's a lot less variation in my interquartile range now. My conclusion? Well, if my conclusion was that I didn't have enough evidence, then with more information, I might now have enough evidence to be able to say that there is a difference. Or if my conclusion already was that I've got enough evidence, then that's likely to stay the same. But with bigger sample, we can detect smaller differences between the medians. So there is a whole pile of excellence level ideas, and those are things that you need to incorporate into your report.